Hello everyone, welcome to our pre-calculus pre-recording video. In this lesson, we will expand our idea about rational function and we'll try to connect it with how graphs of the rational function is related with this equation function, how the graph and the functions are related. So let's begin. These are the agenda: reading the graphs of a rational function, real zero, numerator, vertical asymptote, denominator. Like real zero will come from where? It will come from numerator. Vertical asymptotes will come from the denominator as usual. Horizontal oblique asymptotes relative degree. Then we have graphing rational functions. So more or less all these things we will discuss. And look, the thing that you already have learned, everything is applied here again. So like let's say about the vertical asymptote, all the things that you have learned is true here also. Okay, about the horizontal asymptote or oblique asymptote, all of them are true here as well. Okay, so let's look at the thing. First of all, reading the graphs, let's look at this thing. So you will notice in this graph, first of all, if you look, you will notice a couple of things. Let's bring other part. Okay, so in this graph, you will notice a couple of things. One of the thing is here you see x-intercept. Okay, x-intercept. X-intercept is where? X-intercept is at 0. So if a rational function is given something that let's say we do not know, from where we will get this? We will get this x-intercept. We will get the x-intercept from our numerator. In this case, x-intercept is 0. That means just only x you have here. That is the idea. Okay. And then you see there is some kind of the graph is, this graph is like this part of the graph is like this, and then this part of the graph is like this. So it looks like there is something here. It looks like there is something here towards which the graph is trying to approach, kind of vertical asymptote here. And of course another one here that you may already have noticed. So these two, vertical asymptote, because how do we know that? Because you see the graph is coming closer and all of a sudden the graph almost acting like it is straight, but of course it is not. It is coming closer and closer to that this black color line. So they are the vertical asymptote, and from where in the function we will get the vertical asymptote. You know, vertical asymptote we get from our denominator. Here. For this line you will have something here, and for this line you will have something here. So this value is at 1, so it must be x minus 1 because it is plus 1, so it must be x minus 1. The quantity here, the thing here will be, the term here will be x minus 1, and this is minus 2, so it must be x plus 2, because you know if it is plus 2 the asymptote is at minus 2, if it is minus 1 the asymptote is at plus 1. So you see, this is, of course, this is we will extend the idea a little more, but to give you the very basic idea, starting idea is, okay, to get the x-intercept you get it from the numerator, vertical asymptotes you get it from the denominator. Okay, all these things is written here as well. Yeah, you can feel free to read them. So this kind of something. But see, we do not know if there is like some power here, power of x, power of x minus 1, power of x plus 2. What is the power of this? Or what is the power of this x? How do we know? So let's look. See this how it works. So notice that we have a couple of things here. This is the graph. This one is the graph here. This one is this graph. This one is this graph. When the power of x is 1, then you see this graph. When the power of x is 2, then you see this graph. Just look at this part. Don't care about the other parts here at this point. Just only look at this part. Just only look at this part. Just this part. Just this part. Just here. Okay? Because we are now trying to understand what happens about this x square and x cube. Other part we will discuss is coming. So when it is x, the graph is somewhat crossing. When it is 2, the graph is at that point touching. When it is 3, again crossing. So see, now we know that if it is cross, then the power must be 1 or 3. If it is touch, then power must be 2, maybe 4 also possible, like some even number or some odd number here. So from touch or cross, we understand this. Okay, so we can look at the power. We can look at if the graph is given, we can look at the graph. If it is cross, then it must be the odd power at that point, odd power of that x. If it is touch, it must be even power there. Okay, and then what about the other part? Let me mute it. I won't look at what's going on there for sure. Now look at the other part. What happens there? Let's say in this kind of situation where you have x minus 1, x plus 2, if you have a square here, what happens? If you have a square in the both part, what happens? This is easy, by the way. Don't get scared by looking at, oh my god, all this crazy graph. How do I solve? What can I do? Okay, don't get scared. You see, the technique is super easy. First of all, you all are sure about like why this is x minus 1 or what it does here. It is actually some asymptote here, right? Some asymptote here. This is actually this x minus 1 is doing, because at plus 1 there is asymptote. Same thing here, at plus 1 you have some asymptote here. Same thing here, at plus 1 you have some asymptote here. Kind of, okay? And of course, at this is x plus 2, so at minus 2 also you have some asymptote. Let me draw it some other color just to make it little clear. I mean, the graph will be just some millimeter, not some millimeter, I think some less than a millimeter left side. Okay, so see what happens. This is not hard. See, this is easy. X minus 1, so this is about this this red color graph, red color line, a vertical asymptote. Okay, vertical asymptote. Now see, when this red color graph is here, and see the other the graph that is coming towards it, it is coming like this, and the other graph was going down. And see what is here, both of the graph was coming up from the going up towards that x equals to 1. This is our x equals to 1. See, this is our x equals to 1. Here, if the power is 2, then both of the graph is going towards it in the same direction. It can go down also, but it will happen in the same direction. So, but if the power is 1, then it is going in the opposite direction. This side is going up, this side is going down. Okay, if the power is odd, then see, this graph is going up, then this side of the graph is going down. about for that vertical asymptote, for this asymptote. So for one asymptote, if one side is going up, another side is going down, that means the power is odd. For one asymptote, if both side is going up or both side is going down, then it is even power. Just like this one also. See, this is going up, this is also going up. I mean two lines going in the same direction. That's why power is even. Here, so you see, just to compare, it is a good idea to compare it here, because see, this is x plus 2, power is 1. So power 1 means it will have two different direction, and it is true. See, this is going up and this is going down. Okay, so we will look at the asymptote, this vertical asymptote part. If we see the graphs is both of the side of the graph is going to the same direction, then power must be even number. If they are going to the opposite direction, this is going up, this is going down, just only one line in one side, this is up and this is down, then it must be odd number. Odd number means 1, 3, 5, anything can happen. We do not know what is exactly that number, but we know that that is odd number. And here, if both of them, see, both of them going up, both of them going up in the same direction, here also actually, here you see both of them is going down, so down is also possible, but both, see, two red line in the same direction. Okay, that's why power is even, an even number. So actually it gives us a lot of information. So you can see odd go in opposite direction, and for even they will go in the same direction. That is the decision here. So what do you know about this? You see, this is a x-intercept at 0 and another x-intercept at 1, 2, at 2. Two x-intercept. At 0 it is cross, at 2 it is touch. So we have two information here. Then we actually have a horizontal asymptote also here. As you can see, there is a horizontal asymptote here also. Just by looking at the trend of the graph, where the graph is going, it is going towards this one. Then a vertical asymptote here, another vertical asymptote here, just by looking at the trend of the graph. So here at 0 it it cross, at 2 it touch, then goes in opposite direction. As you can see, this is going in opposite direction, this is going in another direction, this is up, this is down. So this asymptote must be what power? This asymptote must be, there is an asymptote in between these two lines, there is asymptote, that asymptote must be odd. Okay, here both of them going same direction, so must be even, power must be even. There is a horizontal asymptote here at y equal to 1, so this line. So if you combine all of them, you get this equation. Let me break it down once again here. First of all, here for this point you get x, because 0. For this point you get, this is 1, 2, you get, this is x, this value is plus 2, so you get minus 2. And this is touch, so power is 2. This is cross, so power is 1. Okay, now you have something like some asymptote here. This asymptote is at 1, 2, 3. Asymptote is at 3. This is plus 3. So this must be x minus 3. This must be x minus 3. And going in the opposite direction, so power must be 1 or 3, like that. So let's keep 1 at the beginning. And sometimes it can be 3, 5, etc. also, which we can verify later. We have two class on this graphing, so this is the first class, so we will be just, that's why we are just looking at the core concept, main ideas, etc. And there is another asymptote here at minus 1, this minus 1 asymptote, vertical asymptote. There is a vertical asymptote here, kind of this at this line at minus 1, so it must be plus 1. And then both of the thing is going to the same direction, that means power is 2 or maybe 4, etc., etc. But roughly this is our function. And there is a horizontal asymptote here, which is at y equal to y equal to 1, y equal to 1. And how do we know that this horizontal asymptote also matched here? See, we know that if the power is same, then horizontal asymptote will come from the coefficient. The power of the numerator is x cube, because this is x square and x, so x cube, and power of the denominator is x and x square, that means x cube. So power is same, this is 1, this is 1, that means y equal to 1 is the horizontal asymptote. So that also matched. Okay, that also matched. Now let's say in some extreme situation this power is not matching, then you have that option. See, we said that you can actually change this power. This power is an odd number, any odd number. So you can write here 1, you can write here 3, you can write here 5, or you can do the same with the number down here. Okay, so to match with the horizontal asymptote if needed, but that kind of thing we may come in future also in some precise order. Okay, but just to give you an idea, this is how our horizontal asymptote also match with our given question. Okay, and let's look at another graph here. So you know this is the graph and this is the given rational function. So now we know that this one and this one is exactly correct. So think about it. What will be the equation of this graph? And when you think about it, let me actually show here. This is a little tough to see. Consider it like this. Consider it cross. Consider this point touch. Little bit hard to verify it here. And there is no horizontal asymptote here or oblique asymptote here, because as you can see the graph is actually showing like some parabola in this part, like a parabola. That means that there is no horizontal or oblique, so we will not have to consider that part. Just think about what is the x-intercept, what is their multiplicity of the x-intercepts, then what is the asymptote, is this going to the same direction or opposite direction that way. I think you have got some idea about the answer also. Same direction here, opposite direction here. This is cross, this is touch. So think about it. What can be the answer of this question? Okay, and we can discuss the answer in our during the class time. So this is also two questions actually relatively easy compared to the one that we have solved. So try to find out the rational function which this graph resembles. This graph is expressed as. Try to find out that function. Now kind of puzzle. Let's say you have a car. This is something like coming from video games or something. Let's say you have a car and you want to solve this puzzle, and there is a couple of rules here. First rule is pick up all the coins by driving through them. So you will have to drive through them and pick up all the coins. And stay close to the wall. You will have to stay close to the wall. You cannot just like go here and then come back or something like in the middle. You will have to stay close to the wall. That is the condition. But don't hit any of the walls. You cannot hit any of the walls. You can go through the doors or jump through the portals to avoid the walls. So let's say there is a portal here, so you can just come here and like teleport it. You can come back to this box from here to here through this and this. So these are portals. Or you can go through the doors also if there is some doors in between. The car can go only from left to right, from this direction to this direction. So these are the conditions. So you will have to grab all the coins from here. How do you do that? And is this a puzzle game? No, it's actually represents the rational function. See, this wall, they are actually the your vertical asymptote, horizontal asymptote, that kind of thing. You have to stay close to the wall. That means you will always have to stay close to the asymptote. The line comes closer to the asymptote. You cannot go back. go around, because if you go around, go back, then actually it becomes some uh, it violates the definition of the function. Suppose, let's say, just to give you an example, suppose let's say, just to say, suppose if you go there and if you come here, then actually it is not a function anymore, because if you draw a vertical line, then this vertical line cross here and here, then actually it violates the definition of function. So that's why car cannot do this kind of thing. As long as it do not violates the definition of function, then it's fine. So that's why it cannot come back here. Okay, so for example, this one, it can be like this part, maybe, okay, something like this. It's possible because now it's a function, and it follows the rules. It is, the car is coming is closer to the wall, so all good. And also it is touching all the points available here. So yeah, so somewhat related to our rational functions, but it is a very good analogy to visualize what goes on here on the rational function. Yeah. So now let's say all these points are given. You will have to include all the blue points. Approaches to asymptotes never intersect vertical asymptote. Only intersect horizontal asymptote when it is marked. Here it is marked, so you can intersect this. You can go through this. Blue points passes the vertical line test. No x values have more than one y value. So like you cannot just go and come back. That's not possible. So which one of the graphs are correct based on these points? Look at this. Is this a correct graph? We will not tell you the answer now. We will discuss these answers in the class. Is this a correct graph? This one? And why not? Suppose if it is not, why not? And then, is this a correct graph? Why or why not? Okay, think about it. Now we have some graphs here, some points here, dots here that we will have to draw. So in the points in the left side, we will show you the solution of this part. Points in the right side, you will have to do it by your own. So this is the solution for this part, because as you can see, if we want to connect these three dots, see, suppose you can say, sir, if I want to do it this way, now you cannot go through that. Do you understand? Because it is asymptote and there is no point given on the asymptote. If they give us a point, then we can do that. But there is no point given, so we cannot go there. That means we will have to come back here. We are not going left and right. Not like this. This is still satisfying the definition of function. It is still satisfying the definition of function. So no problem. And here we have only one point. So the graph must be like this. Okay, so that's why we have this shape of the graph. Now what will be the graph of this side? You will have to think about that. You will have to draw that. Then for this part, what graph can we draw? What graph can we draw? See, only one point is given. So sometimes, like if you think about your linear function modeling, linear function graph, you may think like, oh, I have a point here, I have a point here, so I join them. But no, here you cannot do it. There is two asymptote here. So asymptote are like walls. You cannot pass through them. And also you will have to stay close to the asymptote. So the graph may be like this. Like this. Maybe this is the graph. And then this graph is like something like this. Kind of, okay? And you will see the solution. Yes, this is the graph. This one you will try to draw. Of course, we can discuss the answer. We can show you the answer during the class time. Not now, because so that you have some time to practice and you have some time to think, which is most important in mathematics. All right. So here we have 2 points. Here also we have 2 points. So what will be the shape of the graph? Think about it. I will show the answer of this part now. Ta-da! This is the graph. Now you will try to draw this one. This is the participation quiz part. So yeah, write a rational function that matches the graph. This graph, not too hard. You have some intercept here. You have some asymptote here. Then you have some asymptote somewhat here. Vertical, horizontal. Think about all of them. Okay, think about all of them: horizontal or oblique, vertical or asymptote, behavior, real zeros, and near behavior. So this will be in our participation quiz. Try to get the answer. Try to think about what can be the answer, and then if you are confused, you can discuss them during the class time. But in all the cases, in all the situation, rules remains the same. Suppose the rules that you have learned in the last class will still will be using it, and the rules that you are learning now in this lesson we will be using it in our next lesson. Okay, all the lessons are connected. See, in some way we actually discuss that linear function, how that concept also we can use here to make a contrast about the concepts. And this is how the concept from one topic and another topic, sometimes you will need to make the difference, to think about the difference, think about the similarities. Anyway, so have a good day, everyone. All the best, and see you all in class. Happy math practice. Bye bye.